Dear students, today we'll see about the theory of acid-base indicators. The learning objectives of today's class would be that at the end of this lesson, the student should be able to describe the difference between an endpoint and an equivalence point in an acid-base titration. They should identify the correct choice of indicators. They should know to illustrate the theory of acid-base indicators. Before passing on to the theory of indicators, let us see some definitions like what is a titration, equivalence point, end point, indicators, etc. Coming to the first definition, titration. Titration is nothing but it is a process where a solution of known concentration is used to determine the concentration of an unknown solution. So the solution whose concentration is known as titrant or titrator, and the solution whose concentration is to be found out or a solution with unknown concentration is known as the analyte or titrant. Equivalence point, the point where the titrant is chemically equivalent to the amount of an analyte is termed as an equivalence point. The physical change occurring related to the chemical equivalence is termed as endpoint. Indicators of the compounds that changes their color near the equivalence point. With these few definitions, let us pass on to the next slide. So at this juncture, let us have a pause, and I want you all to think a while at that. At the equivalence point, what will be the relation between the moles of an acid and a base? You just have a short break, just a 30-second break, and you think a while and come back. Yes, at the equivalence point, the number of moles of an acid will be equivalent to the number of moles of a base. Coming to our topic, acid-base indicators. The acid-base indicators are weak organic acids or weak organic bases that dissociate slightly in aqueous solutions to form their corresponding ions. So the indicator changes the color. It is because of that the ions and the unionized form, they have a different color in different pH ranges. So when there is a change in pH, the color of the solution will also change, indicating when there is a change in pH, there is a change in the color of the indicator, leading to a change in the color of the solution and thus indicating the endpoint. So this table, it shows the pH range, color change of some common indicators. So out of all these indicators, we'll be more concerning with the methyl orange, a weak organic base, and phenolphthalein, a weak organic acid. So coming to theory of indicators, we have two theories that explain the theory principle behind the color change of indicators. One is Ostwald's theory and number two is Quininoid theory. Coming to Ostwald's theory, this is just a few glimpses of Ostwald's theory. So according to Ostwald's theory, the acid-base indicators are either weak acids or weak bases, and the unionized form have a different color than the ionized form, and the color change is a result of the ionization of your acid-base indicator. Your second is quinoid theory. According to this theory, the acid-base indicators are again your weak organic acids and bases, and they have two tautomeric forms which are always in equilibrium with each other. The two forms are benzenoid form and a quinoid form, and they both have different colors because they both exist in their unique pH ranges. So when there is a change in the pH, the colors of the solution also is changed. So Ostwald's theory in an a bit elaborate manner. According to Ostwald's theory, the color change is a result of ionization of your acid-base indicator. The unionized form and the ionized form, they have different colors, and this is because there is a fact called the common ion effect, which is playing a crucial fact here. The pH changes, color of the indicator changes. let us take these two as examples and we'll see how the Ostwald's theory can be applied here. Phenolphthalein, it can be represented as HPH, but for this here in case of equation we are representing it as HIN. This HIN, when it is present in, it is basically in acidic form since it is a weak acid. This preferably exists in unionized form in an acidic pH and it is colorless. So why it is colorless in acidic pH in the sense, since this is a weak acid, the dissociation of the indicator into H plus and free indicator is suppressed by the presence of a common ion H plus, which is furnished by the acid in your conical flask. Now, when the titration commences, the OH minus ions, that is from the alkali, OH minus ions from your alkali will be neutralizing the H plus ions furnished by your acid to water molecules. Now, at some point, there will not be any more H plus ions furnished by the acid. Now, at this juncture, the unionized indicator dissociates to furnish H plus ions and free indicator. Now, at this juncture, the H plus ions and free indicator is liberated. This liberation of free indicator into the solution is seen by a change in the color. Hence, there is a color change from the colorless solution to a basic pink color. So that is what is given as a pictorial representation. At pH 7, phenolphthalein is colorless, but at pH 10, that is alkaline pH, it is pink in color. Now coming to next indicator, methyl orange. So methyl orange at pH 7, that is an alkaline pH, it is yellow in color. It is preferably in its unionized form and yellow in color. Now again, this dissociation of this methyl orange, a weak base, a weak base is suppressed by the common ion OH minus ions produced by the alkali solution. Now, once when the OH minus ions furnished by the alkaline solution is completely neutralized by the acidic solution, the OH minus ions of the indicator is liberated and it gets dissociated into its dissociated form, that is free indicator Me plus plus OH minus. So now this is in its ionized form. It is red in color and preferably exists in acidic pH. Coming to second theory, quininoid theory. So according to this theory, the acid-base indicators occurs into tautomeric forms which are always in equilibrium with each other, a benzenoid form and a quininoid form. They do have different colors and they preferably exist in unique pH ranges. So the pH, when there is a change in the pH, there is a change in the tautomeric form, consecutively leading to a change in the color of the solution. Phenolphthalein, when you take phenolphthalein, it preferably exists in the benzenoid form in acidic pH and it is colorless. Upon adding OH minus ions, when there is a shift in the pH from acidic to basic, the benzenoid form is getting tautomerized to a quininoid form, and this is seen by a change in the color, that is from colorless to pinkish red, and this preferably exists in basic pH. Your next example is methyl orange. This methyl orange, it basically exists in yellow in color, in benzenoid form and in basic pH. When we start adding the acidic solution into this, when the pH is shifting from alkali to acidic side, the benzenoid form of methyl orange tautomerizes to the quininoid form, and this quininoid form tautomerization is seen by a change in color from yellow to red, indicating that the endpoint has reached. And this red form, that is the quininoid red color, the quininoid form, it exists preferably in acidic media. Hope you all understood the area of indicators. Thank you.